Bernoulli's principle. So from equation of continuity we came to know that the mass of a fluid along its flow stays remain constant if there is no sink or source. So this gives rise to a very important relation which is given by Bernoulli, is that the for the fluid in streamline flow, the sum of kinetic energy, pressure energy and potential energy per unit mass will remains constant. But it is only applicable in case the fluid is in streamline flow. So for example, if a liquid is flowing through any pipe, so then the total energy of the fluid will remain constant. So by total energy, what do I mean? The pressure, that means some pressure has been present on the one or the two ends. One must be pumping it to force the fluid to go from one end of the tube and come out from the other tube. Then there must be the motion of the fluid, which is the kinetic energy, and there must be, if the fluids, if the tube is in a different height, a different level other than the same horizontal level, potential energy also will remains same throughout the motion of the fluid. Now, in another way we can explain this is that the sum of pressure energy per unit, sum of pressure head, sum of pressure head plus kinetic head plus potential head will remain constant. Now, what are pressure head or kinetic head or potential head? It is nothing but the pressure energy per unit mass is called pressure head, kinetic energy per unit mass is called kinetic head, and the potential energy per unit mass is known as potential head. So Bernoulli's principle can say that the sum of kinetic energy, potential energy and pressure energy of a non-viscous incompressible liquid in a streamline flow will remain constant. But only has to be very carefully, we have to be very careful here, that this is only applicable to those fluids which is non-viscous, that means viscosity is 0 and it is in a streamline flow. So if the fluid is rotating, then this law will not be applicable. So for any other place where viscosity is present and we try to apply Bernoulli's principle, this is not possible. Then this relation will not work. It only work in almost ideal situation. Now we will see the proof of this relation. As you can see, let us first consider a pipe or a tube through which a non-viscous fluid is flowing through. As we can see that the tube has the section of the tube has a variable area A1 and A2. One end has a greater area, other end has a smaller area, and it is at height H1 and height H2. So at this end the liquid is entering with the velocity v1, on the other end it is coming on to the velocity v2. Now also, as you can see, there is a difference in height, so the potential energy also is not same at the two ends. So now as a result, a pump or something has to work on the side A to pump the liquid or push the fluid through the pipe so that it can reach to the height H2. So that means there is a pressure difference of P1 and P2 at the two ends. So according to Bernoulli's principle, the sum of all these three possible energies should be constant. So in order to do that, first thing is, let us see what is the change in kinetic energy. So change in kinetic energy will be how much? We can write change in kinetic energy will be half m v2 square minus v1 square. The mass we can use equation of continuity principle and change it. So as we know, equation of continuity says that a1 v1 is equal to a2 v2. As it is an incompressible fluid, we can multiply with density both side. So same thing, because mass is equal to density into volume, which we can again write density equal to area into x. In this case it is delta x, so we can call this as delta x. When we use it for this side, it should be delta x1, because here the velocity is slow, so it will cover only distance x1. Here the velocity may be high, so it will cover more distance x2 in the same time delta t. So but in short, the relation we can write like this. So therefore the change in kinetic energy can be written as half A1 V1 A1 V1 delta T into rho. So this x I can change this to rho. Area into x can be written as velocity into delta T. So this is how we are getting this. So here A1 V1 delta T into rho, and then V2 square minus V1 square. So this is the change in kinetic energy. Similarly, we can write change in potential energy. So change in potential energy would be again mg H2 minus H1. So now mass, again we can write A1 V1 delta T into rho H2 minus H1. Now for the pressure energy, you see some work is done at this side. So if W1 is the work done here to push the fluid this side, and W2 is the work with is at the other end, so we can write the change in work done, we can write like this. Definitely here you have to push more to send it to the height H2, which must be equal to W1 minus W2. Now we know work done is force into displacement. Here delta x, generalize it as delta x or displacement. F would be, as you also know, pressure. Pressure is force by area. So that means force must be equal to pressure into area. So I can write this as P into area into delta x. So then we can write the pressure as like this way. So in this way, so we can write P1 into A1 into delta x1, because with velocity v1 in delta time t1 it will only cover a distance of delta x. So that's for delta x1 minus p2 into a2 into delta x2. Now this, using the same relation, we can write v1 into delta 2 for delta x. So let's write it. So we should get here p1 a1 into, we can write this as v1 into delta x delta t minus p2 into a2 into v2 into delta t. Now again we can apply equation of continuity, and this can be written as, because a1 v1 is equal to a2 v2, so we can take this all common out and we can write this as a1 v1 into, oh by the way, these are all small letters, don't misunderstand this. These are small letters only. I should write it, I should be consistent. So it should be a1, this would be a2, this is also a1, this is a2. So a1 v1 I can take into delta t, I can take common. I should get here p1 minus p2. That's the change in work done. So using the principle of conservation of energy, we can write change in work done, because that is the energy what you are giving, that's why the fluid is flowing. Therefore kinetic should be equal to kinetic energy plus change in potential energy. So if we do, we get here a1 v1 delta t into p1 minus p2 is equal to, kinetic energy is half a1 v1 delta t half a1 v1 delta t into v2 square minus v1 square, plus similarly potential energy will give me here also a1 v1 delta t into rho h2 minus h1. You can see a1 v1 delta t get cancelled out from every side. I get p1 minus p2 is equal to half. Okay, here also mass was there, my one simple mistake here. Yeah, density is there, so here also density will be present. Half a1 v1 delta t into rho into rho. So I can take all the common factors out. So half rho V2 square minus V1 square plus rho, I should get here rho, then H2 minus H1. Here delta T is also there. It is A1 V1 delta T rho H2 minus H1. So I should get here rho H2 minus H1. Therefore, if I readjust this, we get this relation P1 plus half rho V1 square plus rho GH. I think I missed the G also. There should be MGH. Yeah, there is a G also present there. There should be G as well, potential energy. So this one should be rho GH. Rho GH is equal to P2 plus half rho V2 square plus rho GH2. This is H1, this is H2. So you can see sum of both sides is same. So in short, the sum of potential energy, kinetic energy, or and the work done per unit, pressure energy per unit mass is constant. This is the famous Bernoullies principle, which with numerical we will try to understand even more better. Thank you.